When I look at this mess, going back to our last conversation about depth and breadth, I start thinking of depth. That was my binary search tree that I started at the top, went all the way down, started to work my way back, and at any point I could go down, I would. So I did the same kind of idea here. I went as far as I could, started working my way back. Breadth, I checked everybody close and then kept checking from there. Breadth was one I think we liked a little bit better. So if I said, let's do this one with depth, first question you're going to have is, oh, there we go. First questions you're going to have is, well, again, with graphs, we don't have roots or anything like that. So I need to pick a starting spot. Alphabetically, we always like to start at A. Looks like B would be a good starting point. Somebody pick a starting point. Again, this is a depth search.
J.
J. We're going to start with J. All right. Give me a letter. First of all, how many are there?
2.
3, 6, 9, 10. I'm sorry. I meant vertices. How many vertices? I think there's 11. So if I can get all 11, I know to stop. So J, give me a number. Give me a J. J. Give me a
E.
The J does go to E. E. Then where?
K.
K.
I can go to K. Sure. Then where?
I.
Want to go out to I? Then where?
G.
And to G. Then where?
B.
I can go to B. 3, 6. I'm at 6 of them already. From B, I can go where?
A.
I can go to A. From A, I can go where?
F.
A can go to F. J's not a bad one to pick. 3, 6, 7, 8. Keep going. From F, F goes to K. Got it. F goes to B. Got it. So now I'm going to start working my way back. Can A go to anywhere unique?
C.
A can go to C. Where else?
D.
A can go, well, I'm sorry. From C, we can keep going depth. From C, can I go to anywhere new? I go to D. From there, can I go anywhere new?
No.
No, so I go back to C. Can I go to anywhere new?
No.
No. From C, I go back to F. Can I go anywhere new?
No.
I go back to A. Anywhere new?
No.
Nope. B, anywhere new?
No.
Okay, so I keep going back one at a time. G, where didn't I hit?
H.
H.
Can't even get the H.
I cannot get to H because for some dumb reason, I have the 2 arrows both going out of there, and at some point, one of them should have gone in. So I either need to wipe this out with white out, or okay, good. Everybody's okay with the depth of search on this bad boy.
So that brings up a good point, though, that we might not be able to get everything depending on, if there's kind of sources or
Correct.
sync. Okay.
Yep. And unlike a binary tree, sooner or later by one of the 3 traversal methods, we could get to it. But here we have 2, and we may never be able to get to H unless, of course, I put the arrow in for next semester and wipe one of those out. But you got the idea. We kept going. If I got stopped, I worked my way back to see if there was someplace else I could go. And then I slowly just kept working my way back. All right. That was the first one. I want to be able to keep this on the screen. And breadth. Where would you like to start at for breadth? Well, I'm kind of feeling bad for H because H got left out last time. So why don't we start at H?
Sure.
Okay. H, where all can H go? What is one path away from H?
I.
I, what else?
D.
D, and what else?
B.
B. So I need to keep these in mind. So I just know they're one path away. Let's go to I. Where can I go? That is also
G.
just to G. Where can D go? Nowhere.
Nowhere.
And where can B go?
A.
B goes to D, B goes to A, and that's it. Okay, so this again, if I'm working on my shortest distance and I look at H and I say, oh, I need to get to B, I should be able to do it in one path. If I wanted to get to G or A, it should be two paths away. Ba-da-ba-ba-ba. Now I'm on G. Where all can G go?
Nowhere.
Just to B, right? And that's already taken care of. A, where can A go? Let go my A go. So I'm at
J.
here. Where? I'm sorry. J.
J. Yeah.
Okay. Where else can A go?
E.
D. Where else? Oh, we already have a D.
E.
E. My apologies. Where else?
F.
I see your pattern here. Where else?
C.
B. I already have B
C.
and D. Thank you. Da 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 da.
We already have D from earlier.
Yes, I do. All right. So now I start at J. Can J go anywhere unique?
You missed C.
Yes, I did. All right. Can J go anywhere unique? Well, what's the last place I haven't visited yet?
K.
K, right? Can J go to K? No. Can E go to K? And as
Yep.
soon as I write the K, I know I'm done because I have 11 vertices up here and I just hit a count of 11. So if I wanted to go from H to K, it would take 1, 2, 3, 4 paths, and it's possible. 1, 2, 3, 4. I got it. There might be other ways, but I can get it by at least 4. So this again, this is a start of an algorithm for finding the shortest path. And just because we started with H, we could have actually started with any letter. Ba-da-ba-ba-ba. Any questions on how any of that works? All right. Next up, we're going to take a look at a program out of the book in NIOF. And we're going to first of all take a look at the data file to make sure we understand what's going on with the data file. In this data file, I have 8 cities. I'm on page 907 in the book. But I have 8 cities: Los Angeles, San Francisco, Denver, Chicago, Boston, New York, Miami, New Orleans. And in each of these cities, it's followed by several numbers. The first number is how many cities does LA connect to? The second number is the city that it connects to. So Los Angeles is going to connect to Denver, Chicago, and New York. So the first thing I want you to do is take a piece of paper, draw the US, draw the cities, and connect them. I'm and then draw the connecting vertices or edges to each of the vertices. Steve and I updated your quick and radix sort.
Thank you.
Can you push the page down so it shows up a little bit clearer again?
Okay.
Thank you.
Peter, I upgraded your programming contest score.
From what?
Didn't you say you worked with Rashik?
Yeah, but I already had a 100 on it.
Yeah, you had a 1 out of 1. No, I gave credit for programs that worked and extra points. So you got more than a 1 out of 1.
Okay. Cool. Thank you.
Uh-huh. Rashik, are you here? Somebody came in late. Alex, are you here? They're not gonna tell me. Alex is here. No Rashik. All right, you need another couple seconds? How you like that side of beef? So let's see. LA goes to Denver, Chicago, and New York. So LA goes to Denver, to Chicago, and to New York. You got that? San Fran goes to LA, Denver, and Chicago. San Fran goes to LA, to Denver, Chicago. Yeah. Denver goes to LA, San Fran, and Denver. That's not very exciting. Goes to LA, goes to San Fran, and goes to itself. Chicago goes to Denver and New Orleans. Denver seems to be a hub. Even though there's a whole bunch of snow out there right now. Boston goes to Chicago and New York. New York goes to Chicago, Miami, and New Orleans. Chicago, Miami, New Orleans. Miami goes to New Orleans, Denver, and Boston. Miami goes to New Orleans, to Denver, and to Boston. And finally, New Orleans goes to LA and Miami. Holy cow. I needed to use some color on this. So using this chart that you see right here, looks pretty good to me. Unless somebody had something better. Go to D2L right now. There's a file there, and we want to get that up and running. This program is going to allow us to do the shortest path. And again, the shortest path is going to be based on what we talked about previously with the breadth search. So in the program, not only are we going to see how this is represented, because we looked at two ways to represent this. The adjacency matrix, the adjacency list. Okay, so we're going to see a program and we're going to see which one it's using to do it. Then, in order to find the shortest path, we're going to be using a breadth search. Coding that we hope we don't have to do because it might take a while. But in the program, it then is going to allow us to enter a city number. It would probably then do all the calculations for a breadth search and then an ending city and tell us how long it took us to get there. Might take a look at some of the code. We see we have a giant file, digraph.h. I see vector in here. I see Q in here. And if I start thinking about my traversal with depth first, how I kept going, and then I would pop to come back to see if I could go any farther. Read the file, display it. A depth first search. Shortest path. A lot of code in this program. Adjacency list representation. I see pushback. There's my vector idea again. Well, not my idea, but discussion. There's the use of a template. This program is like a final exam. Except we're not going to have all of our pops and all of that on it. Shortest path in a network includes digraph.h. Looks like there's only a header file, no implementation file. One of the other things you have to do in order for this to run is go back to what I was showing you earlier in the book. And that was the cities and the numbers that followed it. So if I stop the share, here's the files, the file of all the cities. So you're going to need a network file to go along with it. There. Can you see it, Matthew?
Just move it down a little
There we
bit
go.
more. Yeah, thank you.
Brady, pull yours up.
What's up?
Can you share your screen?
Working.
Matthew?
Mine doesn't like me now. I thought I had it all good, and then now it doesn't like me.
Okay.